Hi, everybody. My name is Boaz. I'm a CTO and co-founder of Jethro Data. And today I want to talk about how to enable interactive BI on Hadoop. So first, let's agree what we are referring to when we are talking about interactive BI. We are talking about a person sitting in front of a dashboard. Dashboard was created probably by a standard BI tool like Tableau, Click, Power BI. And he wants to work with the big data. He wants to aggregate the data. He wants to create graphs from the data. He wants to discover something in the data. That's a human being sitting in front of a dashboard and wants to get the result in interactive time, human interactive time. Now, since you are here, then I'm assuming that some of you have tried to make this happen and have seen the challenges. And there is a reason why this problem of enabling interactive BI is so difficult and so challenging. This use case is very different than other use cases that run on Hadoop. Is working? Okay. Okay. So what we usually do with SQL Engine on Hadoop, we run reports, we run ETL, we do machine learning. And the interactive BI use case is different, and there are three major points that makes it different. First of all, obviously, you need to be interactive. Human interactive time means that you get response within seconds. 3 seconds, 5 seconds, 10 seconds on the worst case. You're not expecting your business user sitting in front of the dashboard to do an interaction with the dashboard and go and drink coffee and return after half an hour. That's not interactive. So you need to respond within seconds. The second challenge is the variety of the queries. You are working with a dashboard. A dashboard is run by a BI tool that generates queries. There is not a person that creates those queries. Those are not data scientists, SQL experts that will create the most optimized queries in the world. And each interaction with the dashboard can create multiple queries that do different things. So you need to cope with the challenge of having different types of queries that are not controlled, that are not humanly created. And the third challenge is the concurrency. When you are working with the dashboard, each interaction, each click on a filter can generate 5, 10, 15, 20 queries. Moreover, you are opening your dashboard to your business users. Sometimes you are opening your dashboard to your customers. You are providing a service that exposes your data to external users. I've seen use cases where there are 100,000 users accessing a service that in the end of it, there is an interactive BI dashboard on big data. So we are talking about a lot of concurrency. And that's very different than what you do with SQL engines like Hive, for example, on top of Hadoop. I'm going to continue to drill down to the challenge, because understanding the challenge, I think, here is the key to understanding why this is such an important problem and why this is such a difficult problem. So let's talk about challenge number one, the performance. So the user did something in a dashboard and it says, this dashboard is too slow. My query is too slow. It's returning after 2 minutes, 10 minutes, 15 minutes. Make it faster. So what do we usually do? The solution for that, the common solution, is data engineering. I'm bringing my data engineering team, my data scientist team, and they start to do things, partitioning, columnizing, denormalization, sorting, a lot of operational overhead. They work very hard, they sweat like this guy. The other solution is to increase the cluster size. Okay, so my query return after 1 minute, I have 100 nodes, let's put 200 nodes, it will turn after 30 seconds. What's the problem? The problem is, first of all, the cost. You're putting a lot of effort, human effort, and time and cost, and you're putting a lot of resources that also cost money to solve the problem. And in the end of the day, data engineering cannot resolve the problem. Okay, so let's say that I have a query that filter by date. So I partition my data according to date. Great, I have a day partition. But the user is a business user. He don't care about your partition. He wants to filter by customer ID, but I partition by date. So what I'm going to do? I'm going to sort by customer ID, but he wants to filter by something else. That's it. So I need to start playing, creating aggregation, creating duplication, but that is not completely solving the problem. That is very expensive, and that's just dimension number one of the problem. Let's see if this works. Yes. Because then we come to the second dimension, the variety of the queries. We have joins. We have different type of measures. We have distincts. We have filters. I've seen dashboards that each interaction can send 15 queries. Each one of them is different. One query runs on those two tables, another query runs on those different tables. One is doing distinct, one is doing sum. So we get a variety of queries. So even if we are able to optimize one query, we cannot optimize the other queries. So what do? Again, more data engineering. Let's try different sorting. Let's try pre-aggregation. Let's try maybe different tables and denormalization. Again, a lot of sweat, a lot of time. And the other problem with that, this is slowing down the business. Because now, in order to do something, the business has to go to the IT or to the data engineering team and tell them, okay, but this dashboard is slow, do something about it. And they spend weeks trying to do something about it, and people are waiting. And in the end of the day, no matter how much data engineering you do, you end up imposing limitation on the application. You're going to tell them, guys, this you cannot do. You can only do this and that, only use the aggregated table. You cannot use the daily table, use the weekly table. You cannot aggregate on that, aggregate only on that. You're imposing limitation because it's not working. Or you are paying with performance. You tell them, guys, okay, you can run your dashboard, but you have to go to drink your coffee because it's not going to be really interactive. So that's the second challenge. And now, let's see, yeah. And this was the second dimension, but we have a third dimension to the problem, like I mentioned before, the concurrency. Dashboards generate many queries. One interaction, 5 queries, 10 queries. I've seen 20 queries sent from a single click on Tableau dashboard. And then with those 20 queries, you're duplicated by the number of users. Maybe it's your internal users, maybe you have a couple of dozens. If it's exposed externally, it can be thousands of users. So even if you manage somehow to push your Hadoop cluster and push your Hive somehow to get results in a reasonable time by taking all the resources, now you have to duplicate this effort by 10, by 100, by 1,000. And this is not working. So yes, you can increase cluster size, but you will never catch up with the business needs. Okay, I'm going to duplicate my cluster, but I need to answer not one query, I need to answer 1,000 queries. That's not even in the same ratio. So those 3 reasons, those 3 issues are explaining why this is such a big challenge and why so many of you are seeing this challenge and find it very hard to resolve it. Just briefly to explain why the existing SQL engines are not so good at solving that. We have amazing technology on top of Hadoop, amazing SQL engines, Hive. There are a lot of very interesting things being done there to make it work better. But in essence, those are general purpose engines. They are trying to solve general purpose SQL queries. They are not specific for this problem. The concept, basically, is the architecture of MPP shared nothing architecture. All the SQL engines in Hadoop are basically MPP shared nothing. The idea is let's do things in parallel. Let's take as many resources as we can for query. Let's exhaust all the memory and I/O and CPU to get something done fast. This is great when you need to run one query. This is horrible when you need to run 100 queries. And those engines, in the end of the day, they will all revert to full scan. I have a query that runs on X amount of columns. Okay, everybody now uses columnized store this way or another using Parquet or org. But I'm going to be fully scanned in many queries, all my data, or at least all the columns in the data. If I have 10 billion rows and 5 columns in the query, I need to scan 5 columns times 10 billion rows. That's a lot of effort. This is how those engines eventually resolve the queries. So yes, you did some data engineering, you saved some of that for some of the queries, but most of the queries will do full scan. Taking a lot of resources, you cannot do concurrency, and many of the queries will return very fast. So now that we understand, again, this is really brief, I can speak 2 hours, why exactly in terms of architecture it doesn't work. We need to understand that we need a different solution for interactive BI. And the way we see that in Jethro is that this solution is complementary. It's not replacing. What being done great in Hive, ETL, reporting, machine learning, that's great. You need something else complementary that will make interactive BI work and work together with those engines. So what we expect from our solution? We want consistent interactive response times. I'm putting here under 10 seconds. It can vary, but it needs to be seconds. And consistency is very important here. If I have a dashboard that creates 20 queries, and I can return 19 of those 20 queries in 5 seconds, but query number 20 returns after 2 minutes, it doesn't work. User will still have to wait for the slowest query. So all my queries need to return in 5 or 10 seconds. That's a big challenge. We need to handle efficiently the variety of those queries, as I've mentioned. And we need to make sure that each query will take small amount of resources, because if each query returns fast, but it's taking all the resources in the cluster, again, it's not going to work. I have many of those queries. Concurrency is something very basic here. Obviously, the solution needs to be scalable. That goes without saying. And automatic. If we are going to rely on data engineering, it's not going to work. We have a business user. He does whatever he wants. He has a dashboard. He takes something, drags there. He takes something else, drags there. We cannot do data engineering ahead of time for that. So the solution needs to do its own data engineering. It needs to be automatic. And another thing, I'm not going to talk so much about it, but this is a another complete section of the problem. How do you handle new data ingestions? Your data is not static. Okay, maybe I did something for my dashboard, but then new data comes in, so I need to know how to handle it and continue provide the performance that I provided for the data set. So this is what we want to have. So before I drill to how we solve that in Jethro, I want to zoom out 1 second and think, in a more generic mathematic way and explain how we approach the problem. So let's imagine the realm of queries. We have, for the sake of the discussion, one table, and the most generic query, the mother of all queries, is select star. Yes, like the mother of all wars, but in SQL. It's select star, that's the mother of all queries. From that query, from the result of that query, we can create other queries, like select some that and this, group by something, and so on. Just a few examples here. If you think about it theoretically, the number of possible queries would be millions and millions. And from each query, from each result set of each query, you can create other queries. You can run queries on top of the results of other queries, like we can see here in the very simple example. Now, the generic SQL engines, we understand the problem. We are looking at the BI problem. What's unique to the BI problem? The thing that is unique to the BI problem, the interactive BI problem, is that there is a human being in front of the dashboard. And this means that the results that you're going to return from the queries need to be human readable. If a query returns 10 million results, a human being cannot understand the meaning of that. You cannot create a graph with 10 million data points. It's not usable. You cannot do anything about it. So when we are looking at the realm of the queries, and then we are asking ourselves, okay, from that huge set of queries, what is relevant for our problem? It's not everything. First of all, it's queries that return limited set of results. And if we break it further, we understand that we are talking about two general types of queries. Aggregations that done on top of low cardinality, generally low cardinality dimensions, or queries that are highly filtered. Queries that have a filter that remove large part of the data set. Aggregation, for example, let's select sum of sales according to date and store. That's an aggregation. Date and store, not very high cardinality. Filter, I want all the rows, maybe aggregated, maybe not, related to a specific user out of my 100 million users. Again, radical examples just to explain the two types of problems or the two types of queries that we are seeing in interactive BIs. So, what we did in Jethro to handle that? Now that we understand the problem and we understand what's happening in this realm. To handle aggregation, the solution is pre-aggregation or cubes. That's the solution. I will elaborate about that later on. To handle filtering, to handle highly granular queries, we are using indexes. the combination of those two acceleration tools enable us to run queries very fast for interactive BI and big data. And the third thing that we did is that we made all this adaptive. We know that you cannot prepare in advance the correct indexes or the correct aggregation. You don't even know what's going to happen. Your business users are going to do whatever they want. So the way to make this solution work is to make it adaptive. The solution needs to learn, the engine needs to learn from what the users are doing, from the queries that are being sent, and automatically generate those acceleration objects and make the whole process completely transparent. So no data engineering. Little bit more about the concept of cubes and indexes. So again, cubes are great for aggregated queries, like the example I gave before. But when we have granular queries, we are filtering on something very granular, we cannot use cubes. If I have I don't know, a session ID in my events table, and I will try to create an aggregation based on the session ID dimension, my aggregation will be in the size of the original table. It's worthless. I cannot use that. So you need cubes, but cubes have a limitation. They solve half of the problem. Some parts that are not useful. That's why you have the indexes, because on the granular queries, indexes will fetch only the relevant rows. You need both to solve all queries for interactive BI. So a few words about how this system works, and then I'm going to demonstrate that. Hopefully the demo will work. It's the demo rule. Let's see if it does. So we have the dashboard. I don't have the user there, but it's in front of that dashboard. And he's sending queries to the servers, to the query servers. The queries are trying to resolve the servers trying to resolve the queries in the best way possible. But they are also reporting to a different server, to a different service, hey, this is the queries that I've got. Can you optimize them? And in the background, what we call the builder server or the maintenance server will generate indexes, will generate cubes. All this information is pushed into HDFS. And the next time the query will come from the user, maybe it will be a similar query. Let's say if now he is filtering by country, by state Florida, next is filtering by state New York. We are going to use the indexes or the cubes that we have generated from the queries that came from this dashboard to make these queries faster and faster. So there is a training mode, the system learns, the system adapts, and after a while, you get what you need. All the heavy lifting is done in the background. And think about the logic. When you run a query in Hive, every time you send a query, you make the cluster sweat. What we do here and say, sweat once. Work hard once, create those cubes and indexes once. Maybe it's more difficult than doing the query, but that's one time at the right. And read time, we are going to do much less work because we have prepared the acceleration. So let's do a small demonstration. In this demonstration, I have TPCDS benchmark data, about almost 3 billion rows, 2.9, 6 dimensions. And I'm going to show Jethro working with Hive, on top of Hive, accelerating Hive, compared to, in this case, to a Google BigQuery. We also had a demo comparing to Hive. It was too slow. But I think comparing to Google BigQuery is a good thing because you got all Google resources behind those queries against one query server of Jethro, one. Let's see. Okay. So this is Google BigQuery 2.9 billion rows, sorry. And I'm going to do something here. That will take a while. So I'm going to do something, the same thing here on the Jethro side. Returned. Let me add more filtering. This returns. This is still running. Google BigQuery on those billions of rows. And I'm continuing to work with Jethro, and each interaction takes 2, 3, 4 seconds. Let's select the year. And the more I drill down, this still returns very, very fast. This finally got back to me, and this is the fastest we could find with about, for Google it took for each interaction from 30 seconds to few minutes. I'll make it more complicated. Again, we need to wait. This is not interactive response time. This is interactive response time. This is what our users expect to see. And we're doing that with a single server and another server that generates the cubes. How I did that, I've created this dashboard. I've loaded data into Jethro, worked with the dashboard against Jethro, clicked some things in the beginning. Some of the interaction took a couple of minutes. Everything worked in the background. And after an hour or 2 hours, in this case, sometimes it could take longer, this is the response times I was getting. And I can, well, I just broke Google BigQuery. So this is how these things work in real life. And it's hard to see that from the dashboard, but the more I drill down, the more dimension that I choose, then at a certain point, the optimizer, Jethro optimizer, will move from using cubes and aggregation to indexes. It's completely transparent, because at a certain point, there are too many dimensions, the cardinality become too high, cubes will not be generated. Jethro will say, okay, this cube is too big, but I don't need a cube anymore. I have 3 or 4 dimensions filtering this. I'm going to narrow down the result set to, you can see on the left, on the right side, the number of rows that actually was scanned. So if with the indexes, I was able to narrow down the result set from 3 billion rows to 78,000, obviously, I can make this run very, very fast. And this demo is, by the way, is a live demo. You can access it. The Tableau demo is tableau.jetrodata.com. We have another one with a click that's called jetrodata-click.com. Okay, we have time. So I'm going to drill down a little bit to the technicalities of indexes and cubes. So the concept of indexes, okay, we haven't invented the indexes, but the way we did that in Jethro is very, very different. Basically, we're talking about inverted list indexes. Those kind of indexes come from the domain of search engines, of search engines and search engine indexing. And the basic idea is that you have your value, let's say customer ID, and it's pointing to the relevant rows that contains the relevant data for this customer ID. So when I need to access the column or the table using the index, I'm only reading the rows or the values that are relevant to me. When I narrow down using filtering the dashboard to run on 78,000 rows, I only read 78,000 values from the relevant columns. I didn't do full scan. That's why it came back so quickly. And the nice thing about the indexing is that the more you filter, the faster you get. When you're using other engines, for example Hive, and you're adding more filter to your dashboard, it's become slower because there is an additional column that needs to be scanned for filtering. In Jethro, you added the filter, great. I just go to the index and I do intersection on the indexes. Now I need to scan less data. So the more you filter, the faster you get. And indexes in Jethro, you create indexes on all the columns. You can create indexes on all the columns. It's not just a single partition that you can sort of, in a way, partition is an index. But partitioning you can do on a single column. Maybe you can do sub-partition, but very quickly you have too many partitions. In Jethro, you create indexes for all the columns. Autocubes. So the combination of columns is done during the query execution. If I have a filter on one column and a filter on another column, what I do is I take the indexes, which are inverted list bitmaps, and I just do intersection. So there is no need to create combination of columns indexes. We do have special indexes for timestamps and for joins. That's one step deeper. I can explain that later. But in general, you don't need it. This is done in the query time. Autocubes. So how does that work? Let's understand the concept. Let's say we have this table, sales transaction, and we have state and some information about sales. And we got this query, select sum where state equal Arizona. So first of all, Jethro will process the query using the index of Arizona, but since we only have 50-something states, we are going to narrow down the result set, but still may end up with something that is relatively big. So in the background, Jethro generates a cube. What is the cube? Generally speaking, a cube is just taking the dimension, the filter dimension, the state, and putting that as the group by dimension. So now I have a table, a cube, that have all the states with the sum of all the prices. That's my cube. Again, very simplified, very trivial scenario. So next time, this is my cube now. I have, for each state, I have the sum of price. So next time a query comes in, I'm using that. This is much smaller table. This is a table with 50-something rows. The original one maybe have 2 billion rows or 10 billion rows. So in this case, I'm going to use the cubes. Again, when the total size of the dimension is not too big. When it's becoming too big, I'll go to the indexes. Well, I guess this is repeating the same thing. So I think the main message in this slide is that this whole process is completely automatic and completely adaptive. I'm creating the cubes according to what I've got from the user, from this dashboard. And one dashboard can create, I've seen cases of few hundreds, maybe a few thousand cubes. But there is not a person that's supposed to create this. Nobody even knows what's happening there. The machine does that for you. And what that means is true self-service. That means that I'm not telling the user, I'm going to tell you what you can do with your dashboard. They do what they want. The cubes are being generated for them. We are not preparing something for them. The system does that for them. So a few words about the Jethro optimizer. Very briefly, first of all, we have a very sophisticated optimizer that takes queries and rewrite them and rearrange them. And the purpose of this optimizer is to end up basically in one of 3 places. Place number 1, I didn't mention that so far, is the result caching. If you have a query, we can cache the results. Now, it's not so trivial, result caching, because we need to consider that there is data ingestion. New data also comes in, so Jethro result caching know how to work with delta. I've cached results for 1 billion rows, and then new data, another 100 million came in. I can use the cache, I can use the delta, and merge the results together. So that's the result caching. I will always try to use that, but in most cases, I will not have that. So then the optimizer will try to rewrite the query in the best way to either use a cube, if it has one, or indexes. Now, let me give you an example of what it means to rewrite the query in optimized way to use indexes. That means that if I have a query generated by Tableau, and I know how many of you have seen what Tableau can generate, you can think about 5 pages SQL with subqueries, joins, subjoins, left joins, whatever, something horrible. You cannot read that. And you have a filter in the outer query. But a filter in the outer query, I cannot use that because I need to run my indexes on the table, which is inside in the innermost query. Moreover, this filter has a function. I'm not asking state equal Arizona. I'm asking sub-str state 2 plus 2 equals something. How the hell am I going to use index with this kind of query? We do that. How we do that? We push the where predicate, we push it to the innermost queries. If there is a function, we use the indexes, the information that we have from the indexes, because we have all the unique values, to scan the indexes with the function and convert the expression to expression that can use index. This is just one example. There are a lot of optimizations related to join, pushing joins out, pushing joins in, trying to push aggregation into subqueries. Many times you will see, again, I'm using Tableau as an example, it's very common. You have custom query in Tableau that is not actually accessing the table, it's something on top of those tables. So you have an aggregation on top of a subquery. But we want to push the aggregation to the innermost queries because we want to run the cubes on the innermost query to make the most generic cubes. So we push the aggregations inside. So there is a lot of things that are being done to the SQL. And sometimes you start with this and you end up with something like that, and sometimes the opposite. But in the end of the day, we will get to one of those 3 paths. And whenever I get to one of those 3 paths, I'm probably going to return results within seconds. and maybe I'll get back to this sentence because I think this is the most important thing here. The best way to speed up SQL query is to do less work. We are not trying to crunch the bit better than others. We have Spark, we have Hive, we have Impala, we have Presto. All those guys, they know how to crunch the bits. That's not a competition. We are doing, I call it SQL judo, using minimum force to get the best results. Few words about incremental updates. Again, this is a topic that we can discuss for hours, so I'm just in a few words to understand. Data is not static. New data comes in, we need to handle that. We have an index that was created on my 1 billion rows, and we have a cube that was created on my 1 billion rows. Somebody loaded new data. So both indexes and cubes know how to work with incremental data. I can run a query that uses the cube, and then on the delta, run the actual query and merge the results. And then in the background, I will update the cubes. So as I push more and more data, I'm still going to get the performance because I do harder work on the delta, but the delta is smaller. Same thing for indexes. I have indexes created for my existing data set. I'm loading new data. I'm creating something that we call an index block. And the way that Jethro indexes work, you can take index block and another index block and access both of them and use both of them for the filtering. So it's a very sophisticated mechanism of handling incrementals and continue to provide the performance. Let's talk about scale. So I've mentioned some use cases. We have use cases with tens of thousands and more than 100,000 users. Obviously, those are not inside the organization. They are external user. For example, medical information provider that provide information for medical specialists in all over USA. We're talking about tens of thousands of people. So we need to scale. So how does architecture work? I've mentioned before that all the persistent data of Jethro, the cubes and the indexes, resides on Hadoop, resides on HDFS. This is the persistency layer. The execution, the computation node are edge nodes. They do compute only. There is a complete separation here between compute and storage. And because those nodes, those Jethro nodes are stateless, you can scale very, very easily. What you need to scale is just to add another node. That's it. The persistent data is in the HDFS. It's a shared everything architecture. Completely the opposite of all the other SQL engines. All the SQL engines are MPP shared nothing. Each host holds some of the data. In Jethro, all those hosts, they see all the data. Okay, and the way we scale up is adding more hosts. Because each query doesn't take a lot of resources, then we run those queries on those only on a specific node, but we can add more and more so we can handle more and more queries, more and more concurrency. Okay, this is the logo, the important logo slide. We have installation in American Express. Symphony is it's important because it's a health solution that opens to many, many users. In Ovalon, I think they have 100,000 users accessing the data. And all those organizations have worked with Jethro and help us to improve the product, and they are using it in production, internally or externally. So that's our partial customer list. And a few words about Jethro integration with Hive 3. So what we're doing, working very closely with Hortonworks. Jethro is a Hortonworks partner. And what we're doing with Hive 3 is we integrate Jethro so it will be hidden under Hive. So today, in order to use Jethro, you need to use Jethro ODBC and access Jethro servers from Jethro ODBC or JDBC. With this, Hive is going to define an external table that will be mapped to a Jethro table. So you're actually going to run the query on Hive. You're going to access from Hive ODBC. You're going to run on a Hive table, which is an external table pointing to Jethro. That means that all your security definitions, if you're working with Ranger or with other security tools, everything that you did in order to protect your data or to define who has access, everything you did in Hive is going to kept as is. The only thing you're getting acceleration, but for you it's transparent. You're working with Hive as you used to be. So that's coming in Hive 3. So, a quick summary, what you're gaining from using Jethro. First of all, is the performance. The problem that we are trying to solve is the performance to make things interactive. You let your user drive the BI by themselves. It's a real self-service. Because everything is done automatically, no manual data engineering, it's all automatically done by the system. You are saving resources. You've taken off the load of the BI, those dozens of queries that run together and kill your cluster. You move them to two or three or four Jethro nodes, and you have taken a lot of, you offloaded a lot of work from your cluster which you can use for other things. So you're saving money, you're saving resources. And you don't need to change your application. We have seen, I'm sorry I don't have this example, but one of our latest installation, we got a dashboard that has, I think, 30 filters, dozens of measures, and then you have a workbook with 15 of those dashboards. Each one of them is different. They try to use that with Redshift. They tried that. They had like 50 categories of data. They put one category in Redshift, ran the dashboard, it worked. They add 10 more categories, it died. Didn't work. They moved that to Jethro. The same dashboard, very complicated dashboard. And they, after 1 week, this was the up and running system with 30 billion rows, running as is. There were minimal changes in the system. We want you to run your existing application. It doesn't mean that we are not going to recommend sometimes to do some things a little bit different to make the system life easier. But in general, we're not going to tell you, okay, we created data model for you, work with that. We want you to work with what you want, with what you have. So that's it. Thank you, and questions, please. Sure. No, Jethro is not open source. Yes. It's a subscription based, yes. It's a subscription based. Jethro is installed on-premise. The question is about the Jethro solution. Is it open source? How is it licensed? And is it subscription? Is it hosted or on-premise? So Jethro is on-premise. It's licensed by server. Yeah, so the question is how we handle incremental updates regarding cubes and regarding indexes. So for the user, for the one that's sending the query, all this is completely transparent. The indexes are being handled in one mechanism, the cubes are being handled, the incremental cubes are being handled in different mechanism. But at any given time, when you completed your incremental load, the moment your load finished, you can access the data, you can run the queries, and you get a response time. There is no downtime. You did your load, it's an atomic operation, you complete your insert into, the system is always on. Yes, please. Mm-hmm. Yes. Yes. This is the question is how we handle a case where the application changed and the cubes or indexes created for the previous application scenario are no longer relevant, and we have maybe a different dashboard, different queries. So absolutely, there is a very sophisticated mechanism of maintaining the cubes. Maintaining means updating them. Sometimes you need to rebuild them, because sometimes you take a table and you overwrite it, you reload a table, so you need to you know that you need to recreate the cubes. And there is a defined place where you keep your cubes, and if the cubes become less relevant, less used, they are ranked by usage and by cost, then you throw away the old ones and you put new ones. So this is being maintained all the time. You don't just keep all the existing cubes, because yes, you can end up with a problem. Any more questions? Yes, please. Yes. Okay, so the question is about the caching. As I mentioned, the servers are stateless, and the question is where do we keep the cache? So first of all, there are two different types of cache. There is query caching. There is query caching and all the special objects that we create, like cubes. All of this, all the results caching, resides on HDFS. It's on HDFS and can be used by all nodes. Then there is files caching. We want to avoid or minimize the round trip, the network usage to access HDFS. I don't want to, if I have a cube that weighs, I don't know, 100 megabytes, I don't want to go to HDFS and bring it all the time. So we're also doing file cache. The file cache is indeed on those servers, but this is just file cache. If I kill the server, it's meaningless. I can bring it up. The file cache will be warmed up very quickly, and the file cache also resides partly on memory. So we have 3 layers: HDFS, files, and memory. We have maybe time for one more question. Yes, please.
Can you spend some words about your project and feeling from eBay? Also an Apache project.
Okay, let's take it offline, because we need to clean the room. Okay. Thank you very much, everybody.